We're going to continue to take a look at the nature of inverses with functions here. Uh, let's take a look at verifying inverses through composition. Please determine if the given functions are inverses of each other. And you notice I'm given two functions as two linear functions here, f of x and g of x. Okay? This is done by the application of a theorem. And that theorem says that if f composed with g of x equals x, and g composed with f of x is x. If these are both true, then the functions are inverses of each other. Well, to apply this, the only thing I need to do is compute these two compositions and check to see if their answers are both x. Okay? So, traditionally, what we try to teach kids is this, in terms of this first one, f composed with g of x. It is meant the same as f at g of x, which means to take g of x and plug it in for x, in f at x. So I'm going to do that in red. I'm going to circle my g of x expression and plug it in for x in f of x. Okay? So what that gives me is it's equal to 4 times the expression I'll write in red, 1/4 x plus 1/2, continuing back in black, minus 2. So that I've set that up to be simplified now, and I'll just do that by distributing and collecting some like terms. Okay? So 4 times 1/4 is equal to 1. Carry the x down. 4 plus 1/2 is 2. Pull down the minus 2, and then you notice the 2's cancel, and I get x is my answer to that composition. And that's good, because that's what I'm looking to happen. But I have to be able to compute both compositions, not just f composed with g of x. I also need to still compute g composed with f of x. I'll do that one in blue. Okay? And traditionally, what we try and teach kids from that notation, it means g of f of x, which means to take f of x and plug it in for x in g of x. So I'll do that with a blue ink here. I'm going to take f of x, the expression, and plug it in for x in g of x. So I'll get that set up here by writing 1/4 times the expression I'm plugging in blue, again, will be f of x, 4x minus 2. And then I will go back in black to 1/2. Okay? So I'll distribute here and get 1/4 times 4 is 1. Pull down the x. 1/4 of negative 2 is negative 1/2. Pull down my plus 1/2. Then I see that those two terms will cancel, and I will just be left with x. Okay? So the formal answer to this, if we see these two computations that both give me x for the answer, is to say, yes, these functions are inverses of each other. Okay? Now, if you notice, I did two compositions here because the theorem says it's got to be true sort of forwards and backwards. Well, in this case, I had two functions that were inverses of each other. If I had it so that they were not inverses of each other, I would know that probably right away, just in the first computation here of f at g at x, I maybe would not have gotten x. Well, if that's the case, I could just stop right there and say that the answer would have been no, that they're not inverses of each other. Because, again, the theorem says that both of these need to be true for it to be a yes, that they are inverses of each other. Well, if you do one computation and it's not equal to x, they can't both be x, so you'll be able to stop right there. I didn't do an example of not being inverses here, but that's how it works. It would be if you did not get x in one of them, which would most likely not give you x in either of them when you do these two compositions. So again, what we're doing is some computational work right here. F of g of x and g of f at x, those compositions, to apply this theorem, saying you have to get x in both those answers for the functions to be inverses of each other.